If you want to become an AI engineer in 2026, you're entering a field that barely existed a few years ago. AI engineering, actually taking models and building real systems with them, that's new. But here's the problem. Because it's so new, there's a lot of bad advice out there. People tell you to spend years learning all the math, master every algorithm, understand everything before you touch a real project. That's going to waste months of your time going in the wrong direction. In this video, I'm going to give you the exact steps I would take if I had to start from zero today, month by month, what to learn, what to skip, how to build projects that actually stand out, and how to position yourself so companies come to you instead of you chasing them. Here's the thing, I learned AI and machine learning in about 3 to 4 months, not master it, but understood it enough to land my first job building prediction models to predict the stock market. Since then, I've built AI software for Apple Vision Pro, I've built AI for a self-driving car that actually drove on a closed course, I co-founded an AI company and went through several rounds of funding. I have multiple AI patents. Y Combinator reached out to me without me applying to join their accelerator, and companies like Apple, Google, Meta, and Netflix headhunt me for AI positions even though I don't apply. But here's what most people don't know. I came from film and 3D animation. I was doing rigging and visual effects. I was a CG supervisor for Teenage Mutant Ninja Turtles Mutant Mayhem. This is not your typical background to get into AI, not even close. So if I had to start over today in 2026, knowing what I know now, what would I actually do? By the end of this video, you'll have a complete roadmap, the exact skills you need, the projects that will make you stand out from everyone else doing the same tutorial, and the strategy to actually get you hired. Let's get into it. First of all, I want to address why is 2026, why is that different? First of all, the path is completely different now. In the old era of ML or machine learning engineering, about 10 years ago, a decade ago, when I started to learn from it, I learned ML engineering. Models were coded from scratch, meaning we weren't using like PyTorch or TensorFlow back then. We actually had to code it from scratch. I built things with Python. I've done it with other things in R, worked with R as well, worked with C, C++, actually building on actual projects. Now, back then, heavy math was required, right? Now, the thing is, I just mentioned before, there's no modern frameworks. Early TensorFlow days were starting to come out, and that was version 1.0 of it. And even then, it wasn't really Pythonic. You had to kind of like create a state and then actually execute on that state. Later on, there was PyTorch, which became more, so TensorFlow was from Google, right? And then PyTorch came along, which was from Meta or Facebook, right? And that was more Pythonic, and then more people went towards that. And then TensorFlow version 2.0 came out, which is working more that methodology. But PyTorch was still, even till today, is still kind of the standard. But back then, pre-PyTorch workflows back then, you had to actually learn the math. You had to learn calculus, statistics, what is gradient descent, forward and back propagation or backwards propagation, what are activation functions, loss functions, you have to understand that, normalization, regularization, things like that, and changing things in log, using changing things in log space and whatnot, because of you could actually take like large data and put it into a smaller range. You have to understand all these things. Now, models already exist. That's the difference today. Models, you have model for almost everything. In fact, they come out so quickly every week. There's one thing on top and then another one comes out, right? So the thing is, after a decade of use and a lot of research going towards this, it's better to just to reuse. That beats reinventing the wheel, right? If it already works, use it, right? And now companies know AI works. The company knows you could get results with them, and they're seeing their competitors getting results. Companies want builders who can actually give them something tangible at the end. They want to be people who are able to implement real systems itself and solve real data problems, right? AI engineering is basically redefined. It's software engineering, but now using AI models. At the end of the day, engineering is to solve a problem, to have an actual solution, a workable, tangible solution that's practical, that's actually being used. Not research or just papers, right? Yes, they are important. Research, blue sky, research, they advance the field, that's important, but at the end of the day, it needs to actually work. So system building is the focus nowadays, right? So competition in this space, so like I mentioned before, in the past, if you just knew ML engineering, you're pretty much good, right? But most likely you have to know the math. Like I mentioned here, you have to know the math here, and you also had to probably go more towards the end of like researcher, right? Now competition is increased massively because AI is everywhere. Everyone's learning pretty much the same type of thing, so it's kind of hard to find the signal from the noise. Then you see right now, because everyone's learning the same things, you have the portfolios that are everywhere, which are identical projects, so there's zero differentiation. So it's kind of like when you have a resume and everyone's saying the exact same thing, how do you know this person is different than the other? I know people who are doctors and lawyers, for example, when they're applying to med school or law school, for example, everyone applying them, if you just look at their resume alone, it looks like the exact same thing, right? And that's kind of like the minimum. Even now, these days, going to use AI, for example, it's kind of like a minimum that if you're applying for the job, you kind of expect that you know, let's say, prompt engineering to some degree, right? So what makes you different versus your competition or the other person from that, right? What is the signal over the noise, right? The main thing is strategic positioning. Taking the example again of like a doctor or a lawyer, their extracurricular activities, the person outside of that, the type of problem, the type of person, or type of how they approach the problem, maybe like say their bedside matters, for example, that would differentiate them from the other person that just knows the generic knowledge. And in machine learning or the AI engineering, just everyone has the same portfolios and whatnot, but how can you actually strategically position yourself that it's actually useful for that company? That is what is going to differentiate you from your competition. So here's your roadmap for your strategic positioning. Month 1, the foundation. So basically, month 1, the first week or 2 of them, learn Python basics, right? Here's the thing, stop learning the wrong things. You basically, if you're going to learn coding and you want to be an AI engineer, learn Python. Python is industry standard, it's non-negotiable, it's a requirement at this day. Pretty much all papers, all cutting edge, everything's written in PyTorch, which is built on Python, right? And personally, like my early Python struggles, I actually learned Python, not really learn Python, is more of I had to use it because of a certain scenario. And at the time, you know, I didn't really know whitespace. It was the first language that whitespace in Python really mattered, and having a tab or you're pressing this space a couple of times made a difference. So that was one of the biggest things at the beginning with me, right? I made so many mistakes. There's a lot of self-doubt, and at the time I had other options. I could have done JavaScript or even did like VB. So because of this pain, I moved away from it. So I only knew, at the time, I was only a beginner at that time, right? Now, the thing is, how I actually end up learning it during the second attempt, because I was literally in a do or die urgency situation where I had like a survival mindset focus where I had to get this done. Python was the only solution. So either you learn it or you pretty much are off the project, you're out of the job or whatnot, right? So the main thing about that is that I knew what I needed it to do. So it's more of like I knew the system design, I knew what the outcome was supposed to be. So I learned Python just in time. So I never actually took like a full course or dependency of it, or like basically take like adaptation. I look at forums, I found code, because like I said, I knew what I wanted it to do. So I looked up forums and looked at other people who implemented something very similar and adapted that. And after a while, you start seeing like a gradual pattern of accumulation. And this thing about this is that if you think about it, right? Children, when they're born, they never go to class to learn how to speak their native language or the native language of their parents or their environment, right? At the beginning, I mean, you learn in school later on to actually learn proper grammar and whatnot. But I mean, to start communicating, an infant don't go to class before they start saying their first words. What happens is they are immersed in an environment and they're seeing, by being immersed in it, seeing people's interaction and the result to come from it, they start picking up the language. This is why if someone goes to a new country and with that speaks another language you never spoke before, after about 2 weeks of being immersed in it, you're going to start learning how to communicate or what certain things mean. And this is basically just in time learning, because another way you can look at it is that you wouldn't sit down and give someone a dictionary and say, read every word of the dictionary and to learn the language. First of all, you already don't know the language. You can't read it in the first place. But second of all, who do you know knows every single word of the dictionary, every synonym and everything on there? It's good to look it up, but you learn by actually being engaged in the actual scenario. And that's what just-in-time learning is that Python, for example, and like I mentioned earlier, stop learning the wrong things. In the context of AI engineering, you're going to learn Python in a specific way in that language. And if you're going to be in that space, you're going to learn what you need for it, right? You're not going to learn everything and every single possibility in Python and web development, like using like Flask or something like that in backend is going to be different than if you're going to use Python for like VFX and using that mainly as a glue of communicating to different software or even general purpose Python of just general workflows and whatnot, right? Just in time is learn what you need to get the job done. And the other thing is reality over code perfection. And of course, if you're taking perfect coding classes and software engineering, and they're very strict on that, they're going to mention this is the proper way. You're supposed to actually log your work and actually comment out all your work with. These things are important, but in reality, shipping beats optimal theory, right? And you'll be very surprised, or at least the general public be very surprised how much actual commercial software or code is not professionally done as you're supposed to do by software engineering, mainly because of the constraints of reality, right? And the perfect solution equals non-existent, because if you think about it, it actually costs time and money to do something perfectly, and I've been in many situations, both in AI engineering and in other aspects like especially game development, right? Where you literally have to deliver to show the publisher the developer has to show the publisher the current build by tomorrow. And if they don't get it done, the project's done and everyone's fired. You don't get funding for the next milestone or whatnot. So you are not going to be sitting down doing perfect code reviews and make sure all the syntax and everything is done correctly and you're following the proper coding guide and whatnot, right? So why I'm bringing that up, because results and working systems, what actually gets paid and what actually gets moved forward, and that is what's important, that they actually deliver on what is expected and solve the problem. And it's very common that you're going to get critics or haters, or I would say haters, who would say that are telling you that, if I would have done I would have coded it in a much better way. And I would say to you, and I mentioned this to other people as well, is that it's true. If you were to do it the way you mentioned it, it would be much, much better. It would be perfect and whatnot. But at the end of the day, my imperfect code that's actually working exists, and your perfect code doesn't actually exist, right? So who do you think the company is actually going to hire to get the job done? One with the actual end results, right? So that's what I would say for like week 1 to 2 of the first month of your roadmap. Now, week 3 to 4, the next thing, following along the stop learning the wrong things, you learn the basics of Python. And again, you could go to many different routes of Python depending on the industry you're doing. But if you're learning AI engineering, I would say that this week 3 to 4, learn the data science stack. And what is that? You're going to learn, these are packages that in Python. There's NumPy, there's Pandas, and then there's visualization packages. The most notable ones are like Matplotlib and Seaborn. So basically, NumPy, it's faster than pure Python. So the thing is about if you're a programmer, you could probably start these flame wars where people like, C or C++ are better because they're closer to, you actually compiles and it's closer to machine language. So it's actually faster, which is true, like C++. But the thing is NumPy, and if you use Python, right, it's like interpreted first, and then, so it's a lot slower. So if you're doing just general like coding stuff, that's fine. But if you need something that's computationally expensive, pure Python is really slow. But NumPy actually uses C++ under the hood. So the actual code was written in C++, but it's an interface with Python, but you don't see that. So the actual calculations are done in C++, so it's pretty fast. Still not as fast as C++, but it's fast enough because it's industry standard for machine learning and PyTorch and whatnot to this date, so it's fast enough to learn. And plus, that combined with, there's also CuPy. Right now, as of now, that is Windows only. basically it uses GPU, like NVIDIA GPUs, and it's very, very similar. It's pretty much NumPy, but it's using NVIDIA GPU. So I've used it in cases where it's literally 800 times faster than NumPy. NumPy is already pretty fast, right? And even NumPy, they have like 3 different libraries of like for architectural. When I say architecture, computer architecture, to speed it up, like BLAST library or whatnot. If you're on a Mac, it might use a certain library on your CPU to speed it up for optimization, versus if you're on Windows or an Intel chip or things like that. You don't worry about this stuff, that happens in the back end. But the main thing about it is NumPy itself is pretty much the de facto calculation or numerical library to actually do fast calculations. You wouldn't use Python and like for loops or things like that. You actually would use NumPy for that. And NumPy, it was created as a free version of pretty much MATLAB. So if you're ever in the actual academic world, mathematics department in academia, MATLAB is the de facto software to do calculations for mathematics and show graphs and whatnot. But I think it's like $1,000, and people couldn't afford that. So at least students couldn't afford that. They're a common person. So NumPy was created. It has very similar syntax to MATLAB. If you ever worked with that, I used to work with that back in like college days and whatnot. And then NumPy was pretty much this solution for that, and it's pretty much the standards now, right? Again, mentioned it earlier, it's the foundation of PyTorch and TensorFlow. So under the hood, they're built. PyTorch and TensorFlow are using NumPy as their calculated numerical library under it, and they build things on top of that. In fact, a lot of things under there as well, you could use NumPy as like types and then convert it to like PyTorch or TensorFlow types and go back. And the main things about this, it gives you the same thing with like MATLAB and all that. They give you some things that if you were to use pure Python or just pure coding in general, just coding paradigms like for loops and things like that, it will take a long time. So I have some examples like reshaping, broadcasting, and indexing and slicing. So let me just bring it here, for example, just so you understand. So if you were to do, let's say, reshaping, that's basically is like representing data sets in a certain way. So just imagine, for example, you had a number like an array of numbers like 1, 2, 3. This is your data, 4, 5, 6. So the shape of this is a range of like 1 row, 6 columns, right? But sometimes when you're dealing with certain operations, that the way the data is laid out matters. So you might want to, and so if you're dealing with one that's shaped this way, where it's 1 row, 6 columns, but you're dealing with data where a data structure where it's dealing in fact with 3 rows and 2 columns. So you could remap this as 1, 2, 3, 4, 5, 6. So the thing is, it's the same data, but now this is 3 rows and 2 columns. So that's reshaping it. It's just taking that and manipulating or reshaping it to another structure. Because this could also go, you could re-represent this as well as it's still 3 rows, 2 columns, but the numbers could go 1, 2, 3, 4, 5, 6. So instead of going left to right, up and down, this is going up and down, then goes to the next column, then up and down, right? Again, the same way, same data, but is represented or reshaped in a similar way, in a different way, depending on the operations. And this happens very, very, very often in machine learning, in just numerical calculations. And NumPy handles that really well, right? Broadcasting, what that basically is that, again, if you're going to do, let's say you had multiple numbers, again, let's say this thing right here, you have 1, 2, 3, 4, 5, and 6. And if you had this, and then let's say you had to multiply each one of them by 3. If you were going to use this normal Python, you probably do a for loop, say 3 times 1, then 3 times 2, then 3 times 4, 3 times 3, then 4, then 5, then 6, or whatnot, and make a loop for that. And again, that's another topic, but that's an inefficient way of actually calculating it. There's ways to calculate the big O, time complexity and space complexity, and in fact, that's part of actual coding interviews. But broadcasting in like NumPy, or like if you use MATLAB and whatnot, you could take a structure and say, take every number in there and multiply it by 3 or by a certain number, and it will automatically just go in and give you a result of, well, that times 3, that's 3, and then that would be 6, that would be 9, that would be 12, that would be 15, and that will be 18. And all you have to do is just broadcast that number by your data structure, and it will give you the resulting data structure for that. So that's very helpful because you don't have to write very verbose code to do that. That's also inefficient. And then indexing and slicing, again, if we go back here, let's say this is our array, you could start saying, well, we have all our data sets. This is small, but imagine if we're dealing with like machine learning, a lot of data sets where you have thousands or millions of data, and you try to operate on it. To slice, you could say, just take this whole data structure, but just slice it from, you have indexing, like, so you have different spots, like 1, 2, 3. If you want to say whatever number is on this spot, you start with index 0, index 1, index 2, index 3, index 4, index 5. It's base 0. That's why in a lot of things in computers, base starts with 0. So if you say, tell me the number in this array that's at index 3, it's going to look like, okay, well, this is the index 3. The value of that is 4, right? So you could go in and get specific data from a data structure by doing this way. Or you could say, I want to slice, give me this basically array or this data, this pack of data, and tell me I want to go from index 1 to 4. I only care, and you could say inclusively, exclusively. So if you, a lot of times exclusive, so it's actually this to here, 1 to 3. So even though you could give it a large data set, right now it's only 1 to 6, like there's 6 values in here, but let's say we had millions in there, but you don't, in terms of computation, again, I talk about there's computation complexity, time complexity and space complexity, or space meaning like memory. If you have a large data set and you have to operate on it, you don't want to copy that a lot of times in memory, or pass by value, or there's a concept of pass by value or pass by reference. A game programming will deal with this a lot because they deal with a lot of data. Same thing with machine learning and ML learning, about that, deep learning. So the thing is about this is that you could say, okay, you have this large data set, but you could only slice and say, only I want to deal with a subset or this slice of it. So it makes it efficient using Python or NumPy, because it will know, okay, I only want this small subset, and will be efficiently calculate or manipulate that. And even though you're not touching the big data set, you could take a slice out of that. So that's knowing these concepts, because these are very common in machine learning, and understanding it is going to be helpful. And that's what I would suggest in the first month, week 3 or 4, to start learning. Pandas, I mentioned that it's built on NumPy, but it's pretty much, think of it as kind of like an Excel-like table. Think of it just like Excel. Let's say you have data in an Excel or Google Sheets. You could take that, export out. Actually, I mean, Pandas can actually import like some Excel, Microsoft Excel files, but you could also export out as CSV file, which is comma separated values. And then you could bring it in Pandas, and you could pretty much do more industrial level calculations using NumPy in the backend, which is more powerful than try to do it directly into Excel. Maybe if you use VB or something like that, but even then, you can start dealing it directly in Python. You could do a lot of things that you could do if you're more of a power user of Excel, like merge and join data sets, concatenate, meaning adding data sets, how to handle missing data. For example, if you're dealing with a POS system, point of sale system, which is common with retail, that you have, let's say, missing dates. How do you handle that? Or missing inventory? If you have to clean your data before all that works, right? There's certain things like group by and aggregate. All these things, these are kind of common manipulations of data that you would do with spreadsheets, and Pandas is kind of like dealing with you could think of it as kind of like dealing with a spreadsheet of data, but instead of doing it in Excel or Google Sheets, you're dealing it with more all the mathematical power behind it, and a lot faster. And the third thing is, once you actually get your data and process it, most times you're going to be communicating this to other people who are not data scientists or machine learning or AI engineers. So you have to be able to visualize and make it to stakeholders, people who actually this matters to, and communicate it in a way that they can understand. And common libraries out of the visualization is Matplotlib and Seaborn. These are common Python packages that visualize data right? And this is used to interpret data, and you have to give it the meaning. This is what the data is, and this is what it means, and why it actually matters to non-technical people so they can make their decision. An example of this, if you ever watch the show Star Trek, The Next Generation, like the second, I guess, in the series, with Captain Picard, if you ever watch him anytime at the near the climax of the episode, there's some type of trauma, like a stress or situation they have to deal with, and he has to make a decision, and he brings his group of counselors and get their opinion, because each one of them are experts in their fields. He might know a little bit of it, but he gets their opinion, and at the end of the day, they, given the data from their perspective, they give their interpretation of what it means, and he is the stakeholder who at the end of the day is going to make the final decision. He's not going to be the ones who's actually going to do all the legwork to figure out how to interpret the data and the recommendation from it. That's basically your job as when we're dealing in this week, dealing the data science stack, is how we're going to interpret the data and give a recommendation to the stakeholder so they can make an informed decision. Because at the end of the day, they're going to make the decision, but you have to be able to visualize and make it understand what it means for them, right? And to give you an example, like my first job when I actually started transition in my first job as an AI engineer, the stakeholders I was dealing with pretty much predicting the direction of the stock market with it, right? And this was given to portfolio managers to make a decision to actually, for their clients to actually make money or not with it, right? So at the end of the day, I was given like signal distribution, explaining all of what that means, and given prediction, confidence in the breakdown, and the backtesting and the interpretation of that backtesting, meaning given in the past, if I use this algorithm that I built or model that I built, how well did it perform? And then the money impact and how much that it framed and how much it performed better than, let's say, the benchmark, like say the S&P 500, right? At the end of the day, they really just care about the impact of it and the interpretation of what that meant. They didn't care about how I calculated it. I mean, I had that in the appendix if they want to know. They never really asked, but it's kind of like if we go to a mechanic. Mechanic might give you an overall explanation of what happens to your car, but you don't want to sit down and watch a video of exactly and them stepping frame by frame or step by step exactly what they did to the car. You just want to know in general what happens. Is it working now? What do you need to know? So they're breaking down the information so you could actually interpret it and you make a decision based off of that. That's basically what you become to do, right? Now, one other thing I want to mention as well is on this roadmap of month 1 for the foundation, you do not need a powerful computer to get started, right? That's another thing people might think, okay, well, and it's a logical reasoning, machine learning, and it's big data. I mentioned before, it's there's space and time. Space and complexity and time complexity of how long things calculate. So how much computation power, how much memory you have. So do you need a gaming computer or that level or anything above that where you need a lot of memory, a lot of GPU power? No, because you have Google Colab, which is free. So Google Colab, if you have a Gmail account, which is basically Google's email, which is free, you could make a Gmail account. If you have one, or if you don't have one, you can make one. When you go into your Gmail account, which is Google's email, right? There's options in there that let you go to Google Sheets, which is a free version, or Google Sheets is Google's very free version of a Microsoft Excel. Google Docs, which is their free version of Microsoft Word. But they also, if you actually click down, there's more options of other things that you could create or that are free. And one of them is called Google Colab or Google Collaboratory. And it's basically what's called a Jupyter Lab notebook. And it's more of a more modern way of coding in the sense that the sheet itself is looks like a Word document, but you can actually have blocks of code that you can put in there that actually execute in it, right? So that code actually works in there. So the whole idea is actually that it's like a documentation that you could if you're reading a textbook, and is explaining how algorithm works, because you have Markdown, you could actually show, like in a textbook, all the explanations, all the graphs, all the symbols and whatnot, and then right after it, you actually executed it and see it work. It's free. There's no setup required. You just create a Google Colab. You could even go on YouTube and look it up to see how it's done if you want to learn quickly how it's done. And what's good about it is that it's free. They have GPUs as available. So if you want to learn how to actually take machine learning models and actually train it, you can actually do that here. And all you need is a laptop plus just internet, right? Because all the calculations are done on the cloud and you just get the results on here. So basically you could start learning all these things as long as you have the internet, and you could go on here. You probably do it on even a mobile device as well. And you could just start learning these things right away. You don't have to have a big investment. Continuing on the roadmap, month 2, learn the machine learning fundamentals. So month 2, these are the machine learning fundamentals. I would not be starting with, well, I would say I said neural networks, but basically I mean like more like deep learning. And that's more of pretty much deep learning is still neural networks, but the thing is, it's more of a buzzword that a neural network looks like, you have nodes that looks like this, right? And then you have them like connecting. If it's dense, like each one is connecting to each other at least once. Anyways, so this is just like a quick representation. So basically this is a neural network. Now the thing is, deep neural networks, if you have more, each one of these, this is like the inputs, right? And then all here is kind of like the in-betweens, all the black box, and then you have, let's say, outputs, whatever. Let's say it's predicting true or false or something like that, or red or green or whatever, how it's set up. Let's say in here, the difference with it is that inside here are layers. Now, if you have more than 2 layers, it's called deep, but it's just, again, a buzzword, right? It doesn't really matter. They're all still neural networks, and this is outputs, right? So now the thing is about that. So when I say not starting with neural networks, what I'm basically saying is that not starting with deep learning, like pretty much really, really complicated neural networks, using where like PyTorch or TensorFlow, you're going to learn the basics. I would say, so this is month 2, so you're going to be learning from week 5 to 6 scikit-learn. So the scikit-learn comes with Python, is a Python package, and it does actually have neural networks built in, but you don't build it, right? They already have models already made in there. They already have pre-built classic algorithms like random forest, XGBoost. You have linear regression, and you don't have to code all these things from scratch, right? You're just going to learn the generic classic algorithms that, in general, best practice is that when you first approach a problem, you apply all these classic algorithms right off the bat, right? And the thing is, people want to skip the classics, and I would say that's a mistake, because they'll go straight right away and like, okay, I want to go to PyTorch or TensorFlow, well nowadays PyTorch, right? And implement the latest paper. And I would say, and in practice, I wouldn't go to neural networks or deep learning networks too early. You want to use a classic algorithm, because you'll be surprised how much the classic algorithms, such as linear regression. So what is linear regression? So let's say you have a bunch of like data points. Let's say you have a graph of like X and Y, and you have a bunch of data points all over the place, right? Linear regression is trying to find a linear line that best fits the lowest distance from every data point to that line. And it will just like have the algorithm will keep like iterate and try to make the best fit of those lines. So it keeps trying until it gets one and said, okay, well, this line minimizes the distance between the distance between all the data points to that line. So now you have this line that if you're going to predict, if I'm given a value of X here, using this line, I can make a prediction of what Y would be. That's what linear regression is in general. And they have other type of regression that's not just linear, but that general idea is try to do a best fit within a data points. That works a lot of times, and it's still a very used algorithm if you use statistics, that's one of the things you have to learn. You actually have to learn how to like write out the actual math equation. The thing is, if you're using scikit-learn, you don't, all these are already pre-built into it, but it's still a baseline algorithm that you should use, because when you get it, you take the data set. If the data set or the way it's structured makes sense to use it and see what it gives you, right? So the main thing, the rule of a thumb approach is start with known algorithms, and at the best, first of all, see if it solves a problem. If it does, great. You don't have to do anything complicated. There's no reason to go use industrial strength, like using a sledgehammer on an ant, right? There's no point of using something super complicated to solve a problem. The main goal is to solve the problem and with the least resistance possible, right? Now, even if it doesn't work, you will still probably want to use a classic algorithm because you could use it as a baseline, and that will be pretty much your benchmark to beat. That you know that even when you're comparing, like I mentioned earlier, when you're showing your stakeholders and the people who care about, when you're giving a recommendation of the approach you take, you could start off saying, hey, we use a baseline like linear regression, and it was not accurate enough. So when we had to go to more complicated measures, and we use our own deep learning network, building a PyTorch neural network, whatnot, right? And you compare the values of the baseline, let's say linear regression versus your custom solution and whatnot. And the thing is, if the baseline works, ship it. If it solves a problem and gives enough accuracy of whatever the criteria was, then that's what you do, right? Classic models still win. It's interpretable, it's well known. Often enough, it solves a problem. And in the real world, it matters a lot. And it does work in a lot of cases. In fact, they're so well known. In fact, you could use it as a catch-all, like a minimum solution, because the one problem with more complicated solutions, like if you're using your own model, is you have to start worrying about more edge cases and whatnot, right? Now, the thing is about this, you learn all the classic models. That's why it's very important to learn scikit-learn. You'll learn the basic skills of how machine learning or neural networks are done, like how do you train and fit a model for machine learning, because how to take a data set, how to do as training and testing data, how you split that out into training and testing data sets, cross-validation setups. These are common workflows that you do, that once you start getting to PyTorch, you have to do this yourself. But scikit-learn, you're still doing the same thing, but you have things into it, so you learn that practice. And also things like feature scaling for convergence. So feature scaling, going back to, let's say, data like I had here. So the thing is, in the real world, you have data that could be all over the place, right? Now, if you take it as is, raw, and then put it into actually, like, let's say, into a neural network to actually converge to a solution, it might take a long time because the range of from here to here is really long, really big, right? So what you could do is actually process it in a way that re-represent the data, so that, like, for example, changing it to log space, where that data is no longer that big range, it could be more like this. And it just is less computation time to converge to a solution, because you're not spending a lot of overhead going all over the place. So think of it like an analogy. Let's say you have a bunch of friends that live all over the city, and if you want to tell them information, you can go and drive to each person, like, let's say, all over the city. Let's say they're all over the city, and drive to each person and tell them the information. And there's a lot of overhead to do that. It will get the job done. It will just take longer to do. Or you could probably communicate with them and say, hey, let's all meet up at this one spot, and then I'll just tell you the information, right? Now, the thing is, you're still dealing with the same amount of people, and the result will still be good, but the thing is, it's more efficient because everyone's now in one spot, and you could just it's a lot easier to process that data in that small space than to go all over the place to deal with all that logistics, right? So you could kind of think of that feature scaling, of kind of processing the data beforehand to make the actual calculations easier, right? And another really big thing is evaluation beyond accuracy. So an example of this, there's like precision and recall and F1 score and whatnot. And again, learn what these are during this month and why it's important. But I'll give you an example of this. I mentioned before, like baselines, right? Where we could use, let's say, linear regression as a common baseline. But let's say we had a prediction machine. We had to make a model where we have as input like our input, we have like different images, and let's say this is in the medical space, and we're dealing with images that doctors will normally look at that and will tell if this picture they see cancerous, like a cancer cells or a thing like that, is it malignant or benign? Meaning, is there cancer there or there isn't, right? Now the thing is, we could have, let's say we make a neural network, right? And then this is our inputs, and it'll be like different features of a picture that it's looking at, like whatever. So this is our inputs, right? And then this is our layers in here, and this is the output. Now the thing is, usually a neural network, the in between, when you have these neural networks in between, this is like a black box. You don't know what's going on. Now this is where like the algorithm comes into place, right? Now the thing is, a baseline, you could have it just say like, no matter what your input is, this is input, right? And this is output, or this is making the prediction, is it malignant or benign? Is it cancer or not, right? That's what you want to know at the end. Now the thing is, you could have in this black box, your algorithm, you can make a baseline that no matter what your input is, you could just say false, meaning that is not cancerous. There's no cancer. So it doesn't matter. You could make your own algorithm that no matter what you have, the output will be false, right? Now the thing is, statistically, this probably be right 99.99% of the time, because most times when images are analyzed, 99% of the time, 99.9% of the time, it's actually false. It's not cancerous, right? Now the problem, so this is where, when we go back to how do you evaluate accuracy, this was a problem, because in layman's terms, when people think, okay, well, this is correct 99.9% of the time, then that means it's a good model, even though the actual algorithm just says output false no matter what it is, or no matter what the input is, right? Then what happens is, and when you use this in real life, it's missing when it actually is that 0.1% of the time where it actually needs to be correct, right? So now there's different ways to measure accuracy on that. Is that not just the percentage that if the output was correct, now you want to start measuring how many false positives were, meaning that we said it's positive, meaning that we said it's true, but they end up being false, right? How much of that is correct? How many, false negatives where we said it's false, but actually is negative, there's different measurements depending on your use cases where you need to be a little more accurate than just doing a pure percentage. And that example of predicting like cancerous cells is one of them from images, is that just saying 99% of the time is false and being correct doesn't necessarily mean you want that as an answer. You want to know why it is and what's missing, like the ones that you miss, why did you miss it? So there's different measurements depending on the use case of this, and you'll learn that in this month, especially with scikit-learn, because there's different scenarios where there's different measurements of accuracy matters, right? And the other thing you're going to learn starting from like week 7 to 8, I would say, is the machine learning reality, is that 80% of it is data work, right? Meaning, like, that's why I mentioned earlier, learn NumPy, learn the data science stack, NumPy, pandas, matplotlib, Seaborn, to basically visualize and all that, because a lot of it is prepping the data, a lot of it is making sure you're training it, you're dealing with that correctly, and you're also feature scaling with it, so it actually works properly. And a lot of it is, then mostly I would say 15% is actually debugging it. When everything's perfect, you have the data, you have the model architecture of your neural networks, you have all the outputs and it's covering correctly, then the actual training of the data, that's only 5%. If all that's all dialed in, that's easy. In fact, if all that's where most of the work is to get this to work, because once this is done, you can give this to anybody, even a junior. They just follow the signs, just follow the formula, and they'll get to the answer, right? The problem, that's not where the challenge is. The challenge is to get the correct data, make sure it's set up correctly, make sure you have correct covering the solution space, and and then the training becomes easy, right? And that's where a lot of the work is. And this is going through all this will during this month will help you go through that process. Now, the pipelines and the debugging, that's where the time sink is. That's where all the energy goes for actual getting received data correctness, make sure the versions don't break in the syntax shift. Like, for example, I've worked on recent projects where just a few weeks ago where I implemented multiple machine learning models that actually, some of them I use AI engineering, some models already existed, so I use that. Some of them they didn't. I actually had to implement the papers into my AI engineering workflow for it. So one paper was more recent, that happened this summer. That's not a problem. There's only a few months ago, but one of them was a year ago. And you think that's not a long time, but the setup of it, a lot of the environment, things change, the data sets change, the way you interact with it change. So the versions break. The code as it was written or how it was described and the algorithms and how it was written didn't work as intended with the current version. So I had to go recreate it, remodel, reinterpret some of the data for it to work. And again, that's where most of the work comes from. So knowing engineer fundamentals, that helps because most of the work was just getting it to work in the first place before I could actually train the model, which again, once all that's working, the training the model is pretty straightforward. It's just a little time consuming, but that's only 5% of it. Most of it is just getting it to work, right? And part of that's why I'm mentioning learning general like software engineering and DevOps and IT stuff is very helpful. Learning, especially in Python, virtual environments. So what's a virtual environment? So you ever had the problem where, or you might have heard, even if you're not a programmer, you might have like certain software where it works fine on your computer, then you go to someone else's computer and it doesn't work, and you're like, well, it works on my computer, right? Well, a lot of times it's because of the environment of the computer, the hardware you have, the version of the operating system, things like that. Now, a virtual environment kind of like creates like a virtual version of a specific hardware, specific operating system, specific versions of packages, and let's say using Python or whatnot. And once you have that, it kind of takes like a snapshot of it. So even if you come back like 5 years later, if you load up that virtual environment and then run code in it, it will work because the environment's the same. Think of it let's say we take the analogy of video games, where back Nintendo, the original one, NES, that was made in the 80s, right? They have specific cartridges that were designed specifically for that hardware. So even if now, I mean, besides that, you do that pseudo blow in the cartridge for it to work, that cartridge is designed for it to still work with that hardware. Now, if you take that and try to put it directly into, let's say, a Nintendo Switch, first of all, it's not even going to fit. Second of all, the software from the cartridge for the video game expects a specific hardware, so it wouldn't work. So, however, if you have like Nintendo Switch or Switch 2, every version of it, Nintendo still re-releases these old games because they have kind of like an emulation, or they take that and have like an emulation to create kind of a virtual environment to mimic like the Nintendo hardware and that environment that software expected to run on the Nintendo Switch. So or Switch 2 or whatnot. That's kind of like what happens with virtual environments, be able to create those. And so you could write code, like I mentioned earlier, where I was writing different pipeline codes and whatnot, or implementing different papers that expected certain setups. By making a virtual environment, you could replicate that setup and save that setup, that you could, anytime you need to run that code again, you just start up that virtual environment so it would work. So this, what do you say, it has version pinning to the certain version of Python, the certain version of NumPy I would use, and make sure all code is compatible. Again, I mentioned it worked on my machine problem. And not only that, virtual environments are reproducible or shareable. So you can give that instructions, especially on GitHub. They explain how to set it up, how to set those things up. And one level above that is like Docker containerization. I would suggest looking up what that is, because that pretty much could do a snapshot of a machine that all someone has to do is just load up that container and everything would work, right? The other thing we'll need to learn is Git source control. Pretty much when you're writing your code, it like when you started coding for the first time, or how you learn most of the time, is that you code all your code into like a file, and that works. That's great. And now when you want to add a new feature, a new feature that the code could do, then for some reason, especially if you're learning for the first time or doing something you haven't done before, you could break your old code and you don't know what you did and you can't revert back because it used to work, but you don't have a copy of it anymore because you just changed your file. Source control allows you to work in a way that keeps track, keeps versions of your code and allows you to add onto it. So basically it tracks changes over time, it recovers broken features. And one of the things you would learn if you learn to Git source control or any source control, there's different ones, but I would suggest learning Git flow basics. So you have like a main branch, a development branch, and a team collaboration. This allows you to actually work with a large team, even by yourself. But I'll give a quick example of how you, let's say, would work with it. Let's say we go here. So let's say you start your code. This is your main code, and you'll have this will be on a branch called main, right? So anytime that you want to actually use your code, and actually use it deploy it in the wild or the public to use, this is the version you give. Now, if you want to develop something new, you will make a new branch, kind of like a copy of it. And this one will be called dev, right? And the things with dev is that anytime you want to do a new feature, you make like a new feature here. Let's say we want to make a window. So the main program right now just makes a window that pops up. There's nothing, and you can just close it, right? Now, so we have a copy of that dev. If we want to now make a window, this is going to be a feature branch that has a button that closes it here. You make a button that goes close there. So this feature would be called like feature button, for example. And then you go in here and you make the code that writes on it. But other people could work on other features at the same time. And when you're done, you could go back and merge back into like the dev branch here, and has the merge of your new feature. And if anybody makes any other feature, it goes into here as well. And then when you're done, you could, I'll just erase this here for a second. When you're done, you can merge all that back onto your main branch, and that's what gets deployed to the public here. So the way this works is multiple people can work on multiple features. They would test it. You would do QA or each feature, depending how your QA, meaning quality assurance, making sure the feature works according to the product. And then it goes back into your main branch and go in here. Now, why this works is because you have versions copies of each one. So let's say you're working on a feature and then now you merge it back, let's say into dev here, and it broke, QA say it broke. Well, you could still go revert back to the version before, and you have to keep track of that. So that's a really quick explanation, but this is the purpose of learning how to use Git source and Git flow, and also how many people could work on the same code base and keep track of that. So again, month 2, learn the basics of how to do this, right? And the other thing is, especially if you're going to do machine learning, you want to learn command line proficiency. Command line, like if you work in DOS or terminal and whatnot, because when you're actually working on it, most of the time, you're not going to have like a graphic user interface. You're going to be working on like a remote server because your computer is most likely not going to be powerful enough to do all the calculations. So you're going to have to like communicate onto the server. And even on Google Colab, they have terminals that you could talk to as well. And you're going to be using XSH to communicate with that. So you're not going to have any fancy graphic user interface or integrated development environment such as VS Code or PyCharm or something like that, right? You have to edit the files in a text editor directly in the terminal or in the command line or whatnot. And so you're going to want to learn these command line text editors like Vim or Nano. So again, look these up on how those work, on basically how in your terminal you could open a text file, edit it in the terminal, and save it and go out there, because sometimes you could have to change configurations on a terminal and you don't have a GUI. So you want to learn how to edit them, save and exit those commands. So on your roadmap, the month 3, this is where you're going to start learning deep learning and modern AI. Basically, this is where you're going to focus more on like PyTorch, and it's more AI focused specifically. But again, you need to learn the basics of Python and some of the basics things of just machine learning in general and data science in general, and some of the other things like Git Flow, GitLab, and things like that, right? Now, week 9 to 10, you pretty much is going to be deep learning frameworks, and you want to be looking at like state-of-the-art papers. And pretty much PyTorch is, I mentioned earlier, is from Meta or like Facebook, and it's more Pythonic. Basically, works more written how Python is designed to work. So when do you want to use deep learning? When does deep learning actually matters? That's when we mentioned earlier why you learn scikit-learn is because they use all the classic algorithms. When these classic algorithm models fail, that's when you want to start going to more like industrial strength, custom solutions. Basically, when you start dealing with like image or text or sequences and all that, that's where you're most likely going to be using like PyTorch and niche deep learning models and whatnot. So the core PyTorch concepts that you want to know is neural networks, the fundamentals, which you learn how to manipulate them, and you're dealing with them smaller scale with scikit-learn. But now you're going to start dealing with more deep learning, so more layers in it. And then data loaders for batching. So the thing is, data is going to be so huge that you can't just load it all in one shot. You could have to do it in batch and pieces. So you can learn how to deal with like dealing with large data set handling, right? The other thing, I learned this the hard way, I could tell you about that, is implementing checkpoints, and you have to do this yourself, and that is mandatory. Meaning, basically, what that is, like basically machine learning or deep learning, you have a neural network, you have these neural networks like this, right? So you have nodes and you have like layers, right? Layers are basically anything from here, that's your input, right? And it makes a prediction or gives you at the end, right? That's your output, right? So anything in between here, these are your different layers. And again, more than 2 layers is called a deep neural network. Now, the thing is about checkpoints is, right, so the amount of nodes you have and the way the nodes and how they're connected, that's what's called a model architecture, right? So when you start using PyTorch, or even if you created your own from scratch, basically the first thing you want to define is a model architecture, and that's saved in a file. So it tells you, okay, the inputs, in this case, there's 4 inputs. There are 3 layers, and these 3 layers, these are how they're connected, and these are how much nodes are in each area, and this is the output, and that's how connected. That description, that's a model architecture, right? Now, I mentioned earlier that inside here, this is a black box. We don't know. So what happens when you're training a model is that there's these values in between the nodes. So when you go in here, is the training part is learning what are the values that has to change between these nodes to get the output that's acceptable, that are acceptable prediction levels, like a threshold, right? So learning is just going here and just changing them and turning the knobs to figure out, okay, these values, if I go into every layer and change the values in here, the output gives me good results, right? These are called weights. So when you're saving out, basically when you're saving a model architecture, when you're saving a model, you're saving a working model is like 1, the architecture, how it's actually laid out and connected, and then 2, the weights, the actual values in here to make the input you give the output that you want, an acceptable output value, right? Now, checkpoints are pretty much saving, in general, is the weights. Some of them is like, I guess you could say, the weights and the architecture. So yeah, I mean, depending on the versions of it, like some, like I think older versions of PyTorch used to just say like the weights. Now you have the option of weights and the architecture. But basically, knowing the architecture and knowing the values of the weights of the architecture tells you the actual model. And that is helpful because usually once you train the model and you know those weights, then you don't train it anymore. You use what's called an inference. Basically, you give the inputs and we give the inputs and it gives you the outputs that you need, right? That's an inference. And also knowing the architecture and the weights, you could convert this you could optimize this and convert this into other things. Like for example, you could train a model in PyTorch, right? And then let's say for whatever reason, now you're working in TensorFlow. You could export out the model architecture and the weights and recreate them in TensorFlow. And that's one thing. But the main thing about this, why I'm explaining this, is that if you're dealing with, let's say, scikit-learn, when you're first learning and you're training a model, they're very small. You could probably train it pretty quickly in like one session, even on CPU, I guess. So like depending on what you're training, because you're dealing with small data sets. However, once you start dealing with deep learning, large data sets, to the point where you actually have to have like data loaders because you can't load all the data in memory, and the architectures are long. It could take hours, sometimes days, to train a model. It could fail. So what happens is that after certain intervals, you save a checkpoint. You're pretty much saving out the weight values. So if you fail, it's kind of like in a video game that you just go back to the last save point or the last checkpoint and then continue training from there. I'm mentioning that because when I first started learning this, I didn't implement checkpoints. So I was training for hours and hours and hours, and then it crashed or the computer failed or whatnot, and I had to start all over. But now then it's learning how to make checkpoints that after a certain amount of intervals, save out the current weights or save out the architecture and the weights. So if it fails, then what you could do is you have a log that checks, okay, this is where it last failed, recreate the architecture, load the weights, and then continue from there. So that's what this does. You basically save long training times. It prevents loss of progress, or at least a little less. You don't start all the way from the beginning. You start from your last save point, and you just resume where you go. You continue. You just continue where you left off, or close to where you left off. Very similar to like a video game, right? Like if you're playing a long game, the reason why you have save points, because especially if you're, let's say, playing an RPG, right? A lot of these games are designed to be like 30 plus hours, 30, 40, 50, 100, 200 hours, right? And you're not going to do that in one sitting. So if you close your game, you're going to lose your save progress. So that's why you save your last point, load where you last save, and continue from there. Or if you died in that game, you'll go back for where it was and then continue, right? And the other thing you got to learn is like CPU and GPU management. These days, all the training is going to be most likely on GPU if you want speed. It's exponentially, like so much faster on GPU than CPU. Just to give you an idea, if you were to train a deep learning model on CPU only, it could take weeks to months. Whereas putting it on GPU, it could take hours to just days to actually train, right? And so GPU is much faster. Now the thing is, you have to learn, and you're going to learn about this, is that the device transfer, there's a threshold, because there's actual time it takes for large data to go load into the GPU, that if your data set is too small, that it's not worth it. The computational hit or the transfer rate and the amount of times you transfer could really take a hit on it. So you want to be strategic. Like if you have a certain amount of data that's past a certain threshold, it makes sense to copy it to GPU, because the time it takes to copy everything to the GPU is you're going to make it up about the amount of computation you make. But if you're like, think of it like this way. Let's say you're going to cook a pot of rice, right? Like if you're going to only take 1 grain of rice, copying it over to one big pot might not be efficient for it. But if you have a whole bunch of it, taking all that and putting it into the pot to cook will be, at that point, it makes more sense. You know, that's that kind of thinking you have to deal with, managing like when to use GPU versus CPU and the time savings with that, right? And these are all just common things that you're going to learn in general, how it works. And then like week 11 to 12, transformers. Basically, the transformer model architecture, that was like introduced in a paper by Google like in 2017. And that is pretty much kind of like changed the ways and why we have LLMs today. And that's why and before that, just to give a small history on that, there's supervised learning. Basically, you would take a lot of examples and you would give it to a model, basically a machine deep learning model, and it will learn just by sheer amount of examples, right? Now, the thing is about that is that it's what's known as stochastic, meaning that each example have nothing to do with each other, which is fine if they're independent from each other. But if you have something that is time dependent, or you need to remember something that happened before. Like, for example, if you're dealing with LLMs or large language models, if you're dealing with a sentence and you're telling a story, you need to know what was said before for it to know the context to make sense. So then other models were created, like LSTM, like long short-term memory, to have an architecture to remember what happened in the past. But then later on, the transformer architecture was introduced, and it is still used till today. And it's important to know how that works. Pretty much transformer powers everything. If you want to learn how it works, I suggest you do. Go on Google Scholar. So what is Google Scholar? If you go to Google and you type in Google Scholar, it's actually another version of Google. Has different search engine types, I guess you could say. Google Scholar is specifically a search engine for academic papers. And if you go to Google Scholar and enter and click on it, it's going to look like Google, but it's going to say Google Scholar instead. Look up the paper. Attention is all you need, right? And to give you a quick synopsis of what it is, basically the transformer model architecture, like a transformer reads all the words. Let's say we're dealing with like LLM, right? A large language model. So the transformer model, it will read all the words at once, not one by one. Each word looks at every other word and decides what matters most. That attention gets stacked over many layers until meaning becomes clear, right? And that's how models like ChatGPT understand and generate language. So basically, one thing about it as well is that it has many attention heads. So instead of one pair of eyes, it has many pairs of eyes looking at it. Like, in fact, if you're doing coding interviews or coding questions, a lot of the techniques would be like you have like a header, or like let's say you're doing a search algorithm, you'll have one head, one person or looks at the beginning of the search and another person look at the end, and you have ways to manipulate that to make it be faster. So this is kind of, you could think of it kind of like that, where the many attention, you have multiple eyes. Like for example, one eye or one head is looking for who did what. Another one is looking for the time. So you have like that relation, like basically like a temporal, kind of like I mentioned, LSTM. So it could have context of like as time passes. And then one of them looks at relationships. And so you have multi-head attention. Basically at the end, once you have all this information, you start mixing this information. And after it starts paying attention to the model, it mixes important information together, and that makes a better understanding of what each word is. That's the high, like really dumbed down or watered down explanation of how the attention model works. But again, if you're going to work in this space as an AI engineer, it's a free paper. Go to Google Scholar. Go to Google and look up Google Scholar. Look up the paper. Attention is all you need, and read it. Just to let you know, again, 10 years ago in the past, I had to read before AI engineering, where models are already created. We had to read a lot of papers and compare them. So there are actual software where called like Zotero, for example, or Medley. These are applications that manages papers. So you would download this, like this would be like a PDF. You get Zotero, for example, you could drag and drop it, and it will basically keep track of papers for you. So then later on, if you're reading a whole bunch of papers, you could go into the Zotero. If it's already in this database because you drag and drop it, you could start searching and it will tell you the paper and it will do the citations for you. So if you're in the academic world, this is very common as well. And like I mentioned before, transformers are the foundation models, ChatGPT, Claude architecture. This is what made it possible, because before this, it was like a leaps and bounds and it made AI accessible to people nowadays, right? Again, with this, like conceptually, you want an understanding of how this works. That's why I kind of gave a quick explanation, because when you read these academic papers, it's going to sound very very technical or very academic, right? So it's not necessarily accessible to the common person, but the high level way it works, it is not as complicated as it seems. And the main thing about this, you just want to understand this conceptually. You don't have to build this from scratch. You just want to know how it works, so you know what knobs to change. Because when It's kind of like, think of it as when you're elementary or primary school, you learn multiplication, division, how to do long division, how to do it all in paper. Or if you're doing linear algebra, you learn how to multiply matrices by hand. But in real life, nobody actually does that. But you know conceptually how it works, because when you actually work with it, like if you're working with Excel sheets or working with math libraries or whatnot, you understand what it's doing and what knobs to change and what it does. That's why you want to understand. That's why you're doing all this stuff. Not because you want to become a researcher, is that when you start working with AI models, you know what's actually happening and what values, what they mean, because you know where they derive from, right? Other things you need to learn that you're going to learn during month 3 here is like LangChain, the framework. Basically, it's LLM orchestration toolkit. And it's for Python and JavaScript support. It's the tool and the model linking. How do you work those together? This is now starting getting into the higher level AI engineering part, right? And then retrieval and augmented generation. So like, how do you get external data access, enhanced model capability, and then agentic workflows. Now this is start getting to more, AI solutions. Agentic workflows pretty much, for example, in the past, they've tried to, let's say, solve everything with LLMs. But the thing is, LLMs, at least at the time of this recording, is like notorious for being very bad at math, even like simple word problems that you probably learn in grade 2. So it will sound confident, and like you say, like if Johnny had like 3 apples and then he lost 2, how many have left, right? Something as simple as that, LLMs could get wrong, right? And you wouldn't know because you'll be confident with the answer it gives you. And then sometimes you have to say like, hey, this is not correct. And it'll be like, oh, I'm sorry. Let me actually use Python backend to do the calculation. That would be an agentic workflow because it's using a tool that augments its reasoning, because it was not designed to do math well, but it could use a calculator or a language like such as Python to do all the calculations, give you the result, and then use language, it's large language models to incorporate the answer and the reasoning within it, right? So agentic workflows using outside tools to do things that it's not strong at really augmented in the recently the power of these models, right? This is, delegating math to tools is pretty much a prime example of that. But this idea expands AI capabilities. So if the model can't do something, you could add agentic workflows, even with like traditional software engineering tools that you have. Let's say you need to process videos, you could use like FFmpeg to process a video and get insights from it and give it back, or back for the LL model to give it more capabilities that it couldn't do before. Roadmap for month 4 and beyond. This is where you start doing real projects. And this is what I highly recommend, and similar to what happened when I was doing it as well. So in month 4, this is where you do real projects. Tutorials stop here. So yes, the first 3 months, it might need explaining it over really quickly over here. Might seem very overwhelming, but these are kind of like the foundational things that once you have that, you pretty much could go in and start looking up things and start implementing it into real projects. You know enough of it to start actually doing things. Now, you won't be a master of it, right? That's you have to know to draw the line that, okay, I know enough that I actually have to start doing things, and I'm only going to learn by getting experience, right? And this is where I would say the hiring process, this is where it starts, because at this point, this is where I would say you start applying for positions. Main reason because you're not going to get responses right away. It's going to take time before you get some feedback. But during that time, you have to accumulate by consistently going out and applying. At the same time, while working on real projects, you are building up your portfolio and your skill set and your confidence as well, because at the beginning, it's overwhelming. There's a whole bunch of things you don't understand of what I suggest you learn for the first 3 months, right? And then now you're applying, you're not going to have confidence because you don't have anything to show, right? But confidence comes from competence. The more you do over time, once you've done something, you're really confident of it because you've done it before, right? You're not really confident at the beginning because you haven't shown any competency in it beforehand. And one way to help with that is actually to start with the domain that you are already an expert in. If you're in a specific domain, combining AI into it gives you an edge, and that's what's going to differentiate you from other candidates, because you actually know the context, you know what success is supposed to look like in that domain, right? So adding AI to it in that context, you're going to win out, right? And domain knowledge is going to be pure AI skills, because companies want a solution specifically for their domain, right? They want to know that real problems can be solved, and you know that you know the correct outcomes and what it's supposed to look like. Just putting AI for the sake of AI is not really going to be helpful. And for me, my personal domain, when I started out, I was, in 3D productions for both AAA games and VFX. So I knew how shots, assets, deadlines, and the politics and the constraints on how all that stuff works. So now when I started implementing AI into it, I knew what the outcomes were supposed to be. So hiring me or putting me on a project made much more sense than putting a pure ML engineer on a project that had no idea how the actual industry worked. And trust me, I've seen this. I worked with a lot of them before, and a lot of things that would be basic to you because that's your domain expertise is foreign to them because it's not their world. And outside of this project, they probably never would interact with it. So they're not gonna go back and learn all the backstory and all the knowledge they need to learn to get up to the space. So pick a domain and be specific with that problem, right? So if you're in fitness, you could be like fitness progress tracking, right? If you're in finance, what are the trends? What are the predictions? I've worked in AI predictions to work with the stock market, right? So knowing what the output and the case in that case, the benchmark was to beat like certain, like let's S&P 500, for example, right? So knowing that space and what that means is really helpful. Like logistics routing, if you're dealing with like supply chain and delivery and things like that, right? The other thing is you want to use, when you start dealing with real projects, you want to use real messy data, like real world data, like real case scenarios, not Kaggle data sets. So Kaggle, if you're doing the plan laid out for you, the roadmap laid out for you, where month 1, month 2, especially you start learning like scikit-learn and whatnot, you're going to be dealing with data sets, and most likely you're going to get it from like Kaggle, because they have a lot of data sets you could use to start learning machine learning or deep learning. Also like consensus from like government, they do a lot of surveys and they give out that data for free. The thing is, it's great for learning and it deals with the overhead, so you could just start learning the tools and how to process the data and how to interpret it. The problem with it is that they're curated, they're already clean, they're already perfect, they just plug and play, they work. In the real world, it's chaos. It doesn't work that way. You're dealing with a whole bunch of data and you have to figure it, and that's the biggest problem, is how do you actually conform the data in a usable fashion, right? Showing you could do that is what's going to make you stand out. That's why doing real projects of how do you get the data, how do you actually massage it and make it work. And not only that, like how do you actually get it? Data acquisition is a big thing. There's AI, there's APIs, application program interfaces and databases so learning how to use those APIs or how to get the data from certain databases, that's part of your real project, because that's what you're going to be doing as AI engineers working with real companies. Or they might not actually have like official databases or official APIs, but the data is on the web, on websites and whatnot. So you have to have the skills of web scraping. How do you read a website, extract the information you need, and manipulate it? And the thing is, websites change all the time. So how do you keep track of that? How do you tell if it's the same or not and validate that, right? And then after, when you get the data, how do you clean it from reality to make it work? So for example, using a POS system, like a point of sale system, where you have different dates and like different date formats. So you might have day, month, year, and another one might be month, day, year. So you have to make sure you have inconsistent formats and clean the data and conform it before, normalize and make sure everything works. This is a standardization, and that's a skill that you need to learn before you actually process anything. So, and companies pay for data work. That's a large amount of it. And data is really important. Data, as they say, is the new oil. That's where the actual value is right now. And the thing is, I would say for this month 4, build a minimum of 3 projects. The first project is going to be messy. It's going to be very frustrating. but you want to get through it. It's kind of like when you do something and then once you don't know what you're doing the first time, but then after you do it, then you're like, oh, now if I knew that, I would do this better. That's why the second project, you know the pitfalls that you're supposed to avoid because you've done them before, and you're like, okay, I've been burned in the past doing this way, I'm going to do it better this time. And then that's the third time, like once you do it more and more, you get more comfortable, and that's where it starts clicking, third, fourth, and fifth. That's why I mentioned do 3 projects, because by the time you get to the third one, you'll be a lot more comfortable with it. And make sure you go end to end, don't skip steps. You want to do the data collection, right? That's the acquisition I mentioned earlier. You have data acquisition. How do you get the data in the first place? Do you use an API? Do you use databases? Do you not have to do web scraping? Figure out how. That's a big part. How do you get the data? Then how do you clean the data? How do you actually conform it to make it consistent and normalize the data, and so you actually can process it? So biggest example be dates. Make sure you choose a format and make sure they're consistent. You don't want them being inconsistent, where you have the day, month, year, the next one, month, day, years. Because the next thing, once you have the data and you put it into your model to train, if they're inconsistent, you're not going to get good results, right? And after that, how do you deploy the actual model that you train? Once you have the data, you have a model that's training, how do you actually deploy it and actually put it out there to people for them to use? And then monitoring the progress to make sure it's working as intended. Now, the reason why you want to use real projects that actually look at companies in your domain that you choose and the problem they actually want to solve is because a demo is very different than a real system, right? Demos are easy. It's, again, when you mentioned about Kaggle data sets, you have curated data, everything's perfect, and when you show a demo, everything just falls into place perfectly. It's plug and play. And the thing is, in real life, everything's like an edge case. There's an exception. Oh, the data didn't work this way. The dates weren't formatted. Dates were missing. So you want to show how your system actually accommodates for that, and then also showing actually people using your system. Adoption matters. You're like, oh, if people are actually using it, that means it works. That means it could work for us. And then because you're also working with real projects, documenting the business value of it is what's going to get the attention of companies, right? Not just the technical details. Again, people who are in AI engineering, they might care about what's happening on the technical side, but at the end of the day, companies or potential employees or potential clients going to want to care what's the time saved, what's the errors that reduce, and what's the financial money impact of this. I'm going to save money. I'm going to make money off of this, right? Because at the end of the day, that's what businesses are geared for, right? And the other thing is, once you make your portfolio on your real projects, and this is how you're going to differentiate yourself, is the framing. You want to show the problem first. You want basically, what are the stakes? Like, why does this matter? And how does it pertain to that person or company, right? Before your solution. Because if you show the solution without the context of what the problem solves and what's the stakes and why it's important, no one's going to care, right? And you want to show the measurable improvement that before not putting this information, what's the problem? Then after, what is the actual improvement that your solution actually implements and does? And then that shows a clear business impact that they're like, okay, we want this impact. That's why we want to hire you. So here's your job hunt strategy. First of all, most fail on this strategy because they believe skills alone will get them the job, and that's honestly not enough. The other thing I would mention is apply before you're feeling ready. And I actually learned this from when I was in university, and I saw the people who actually had jobs right when they graduated, and most people were struggling, and then afterwards, and it took them months, even to almost a year or beyond to get a job. And when I asked people how did they get the job, well, one, they were actually applying the year before they could start graduating. So then by time they graduated, by time they got feedback, they're mentioning, yeah, everything's good. I'm just graduating at this date, so I could apply. I could start afterwards. They started way before. So that's why in this strategy, your first 3 months, you learn the basics. You learn enough of it. You're not going to be a master of it, but then you start applying because you have enough to start working on real projects and start learning from real experience. But it's going to take time before people start responding to you. And then when they start responding to you, your confidence go up because your competence starts going up as well, right? So the thing is, job timelines are really long, regardless of how skilled you are, right? It takes weeks before there's first response, and then interviews are months later, and it could take 3 to 6 month cycle. And not only that, you're not the only candidate, right? So they might go back and forth. So you want to start applying to a lot of them. So when they start rolling in, you have options as well. And early applying creates momentum, right? You're ready later and that's when the offerings starts coming in. So you want to avoid idle waiting by applying now, that when they start coming in, that it start aligning with the competence that you build up and builds your confidence as well. And that's, you're just building more and more portfolios to show them as well. So for me, this was a little different, slightly different. Like 10 years ago, my first AI job, the lessons I learned, like first of all, when I started, I had zero domain experience, but I was hired on potential because at the time I actually knew how to do AI, build actual AI ML models from scratch, machine learning models from scratch, which most people didn't know. And my experience, I did have real world experience in the VFX and 3D pipeline. So knowing that approach was transferable to it, right? Now, the thing is, it's nowadays, because more people know of it, they want to see actually real world projects that are more applicable, right? So like the thing is, by applying as well to a lot of it's a numbers game, right? By applying, it creates momentum, and rejection risk is low. Like the worst case scenario is that they say no of it, right? And they might get applied to hundreds of different jobs, and most of them says no, but you have a chance to say yes. Like, all you need is one yes for it to actually work, right? And then it doesn't matter how many times you fail beforehand, right? And the thing is, month 4, like daily routine, what I've noticed from people who are successful, and basically they do this even for networking. They spend like 1 hour in the morning and they just reach out to people that are in their network, right? And this is the same thing with the people that I mentioned that had a job after graduation. They would basically spend their morning and apply to 3 to 5 jobs every morning for the last year. So by the time they're ready to graduate, they'll start getting things back, but it was just part of the routine. Though that one time they do it in the morning might not seem like anything. They don't expect anything, but it builds up. It's like if you're going to the gym, right? You're not going to see results at the first time you go, the second time you go, the first week or the second week, right? But if you go consistently and stick to it, it starts adding up after 3 months or 2 months or after a couple of weeks, right? So basically, the thing is, the morning, the basically approve one project, like apply. Well, in this case, like that's one way I suggest to do it. You could, in the morning, you could approve one project at a time. The reason why I've said in the morning is because a lot of time you're thinking, when people wake up, your thought process and your thinking is probably the sharpest. The reason why I'm looking at this, because I know a lot of people usually when they come in, they start their day, they start applying for jobs first thing in the morning. You could do either one as long as you're consistent with it. But I put morning first because people are usually the most focused when they wake up. And then lunch, they start going down a bit. And then like evening, you start building or start learning start doing research on what to build or do next for your real world projects to build out your portfolio, right? I mentioned earlier the routine compounds over time. Successful people always time block out their mornings. They basically, you schedule in what you're going to do, and during that schedule you focus in. You don't take any calls, you don't doom scroll, you do what you're supposed to do during that time, and it adds up over time, right? Why I mentioned doing it early, because of silence. Like, it's early on. I mentioned early, I meant early on. By doing this stuff at the beginning, like it builds up over time. You're not going to see anything at the very beginning, but then by doing this consistently, all of a sudden, it might seem like all of a sudden all these people are applying to you and all these things are happening. It's just that it just builds up over time. And the other thing I'm going to say is apply beyond just tech companies. Every company needs AI, right? Search for keywords like ML engineer or machine learning engineer, or data science or AI engineer. Any of these buzzwords that anyone mentioned, just apply. A lot of these companies don't know specifically what they're looking for. So even sparking conversation could spark an opportunity, right? And again, target your domains and companies because you know your domain, you know what you could easily talk the same jargon with it, and then adding AI to it, they make it more believable because they go, you know your space, but we don't know AI and you do. You could be, the savior for and solve the problems you're looking for. So if you have a healthcare background, look for healthcare firms. If you have finance, look finance firms, same thing. Any domain knowledge is your edge. That's your superpower, right? And then for interview focus areas here, that you wanted to show if you have implemented research papers, or at least show models that worked on these papers that show the recent papers, especially the ones on the transformer architecture. I mentioned look it up in Google, and you want to be able to translate these concepts to code, or at least a working model of it, right? And be able to explain it. So in my example, my job actually use real financial data, because when you're actually going to be working on a real world projects or real company, you're going to be working with real data, right? And you want to show that you handle messy real world data, because in real life, data is inconsistent. It's going to be missing values. It's going to be weird data structures. You have to show that you know how to handle all those stuff. And one of the biggest skills, you have to be able to explain to non-technical stakeholders. And in my case, I had portfolio managers, and have to frame it how this data and this model, what is giving us, and how to interpret it, and why they should care. And in my case, why should they buy, or they should sell? What's the implementation? What's the recommendation for them to make an informed decision? And then at the end, you want to be able to connect the AI to the business values. At this day and age, 10 years ago, people just wanted AI in general, or machine learning in general. Now you have to show how the AI actually gives the business value, show the impact before and what is the impact afterwards, and how it actually solves their problem. I want to share the uncomfortable truth that comes with a job hunting strategy, right? One, I'm not going to lie to you, the timeline may be longer. It could be 3 to 4 months. That was my personal, right? But it could be 6 to 12 months, especially with the economy, things that could be happening at the moment, that something that last year, they'd be hiring you all the time. They're looking for people, and then something happens and they're not at least this season, and then it happens again, right? So you have to understand it's going to depend on the effort you put in. If you put in zero effort, if you don't put yourself out there, you're not going to get any job offers. But also depends on opportunity. No matter how great you are, you could be a genius and invented the new model architecture, but if there's no opportunities, nobody's hiring, it doesn't matter, right? So think of it this way. Just imagine that you're a homeowner and you have a pool, and you live in a city that has seasons. So you anticipate that during the summer, you're going to need someone to open your pool and maintain it and whatnot. And locally, you have different pool companies that maintains your pool. So you communicate with them, and they're anticipating, oh great, we're scheduling in a job for the summer, so they expect certain income. And then summer comes, and then you realize that your family and your friends and all that are going to be traveling all summer, so you're going to be at beaches, and you're never going to use a pool, so the opportunity is not there for them, right? So regardless of how skilled those companies are, and they anticipate and you communicate, it could be that, well, there's no longer any opportunity because we don't need it anymore. And this happens a lot with companies, where you're talking to a company and they're like, it's great, and then later on you think you have the job, and then later on they're like, okay, well, we no longer have an opening position for that because we're going in a different direction. We're not going to go there anymore. So don't be surprised with that, because that happens pretty often, especially with AI, because people know the buzzword and they wanted to solve certain things, but they don't exactly know what it is exactly. And then after further discussion, they might come up with a different strategy or hold off on things. So that's why the uncomfortable truth here is that, I say 3-4 months, it could be 6 to 12 months. It's going to depend on what's actually happening, right? But the thing is, starting is non-negotiable, right? If you don't start, there'll be no outcome. If you don't apply, no one's going to hire you if you don't apply for a job, right? So really, the only path is to keep going. If you're serious about actually getting a job in AI engineering, you're going to have to keep doing it. And you're going to fail many times. You're going to fail way more times than you're going to succeed. But the thing is, you only need to succeed one time. And that one success is going to erase all the other failures beforehand. and results can flip suddenly, right? So before, everyone doubts you, and I can tell you this from experience many times. In fact, probably every project I've ever worked on, everyone say you're going to fail, it's not going to work and whatnot, until you break through. Then everyone jumps on the bandwagon, right? Struggle is going to become invisible later, because once it's working, everyone forgets to struggle. People forget early failures. I could tell you that for a fact. And if you want an example of this, Steph Curry, which is the greatest three-point shooter of our time, right? I'll give you an example of the Olympics this year, right? So during the Olympics, not this year, the past Olympics of this, right? During the Olympics, right? He struggled. Like most of the games, his shots weren't dropping. In fact, all the sports analysts, basically they're just critics talking about saying, is he going to show up? Is he going to work? He's not delivering on whatnot, right? And then the last game, they're playing in the Olympics in France, and they're playing France for the final game. And it was actually a close game. And they were even double teaming Steph Curry, and he made this ridiculous shot that, by all intents and purposes, is actually a bad shot, but because it's him, it's fine, because Steph Curry is one of the greatest shooters of all time, right? And not only that, it was poetic because he hit the shot, he won the game, it was against France, and the thing is, France played well, they did everything perfectly. It was just that he did that such an outlier type shot that worked. That one clutch moment is what everyone remembered, right? And the thing is, afterwards, you hear how this is on every news outlet, and the same people who were doubting before were saying, like, these same sports analysts, is he gonna show up? What's he doing? They're saying it's the greatest shots ever. This was probably the best game they've ever seen, the best shot, the best moment ever seen. And that's all people remember. Everyone forgot about what happened beforehand. Then the moral of the story here is you only need to get there, right? And failure is a part of the path. That's just how it works, right? And the thing is, as well, is that competence, I would say at least, competence is what creates passion. And passion is what follows skill, right? So a lot of time people say, like, if you're confident, if you're passionate about something, you're not going to feel like a job right now. But I do believe that confidence is what fuels motivations, right? So at the beginning, you're going to feel overwhelmed when you first start at, the month 1, month 2, month 3 plan, the gradients, the matrices, the back propagations, activation, all those things, right? Activation functions and things like that. It's overwhelming. It's overwhelming for me, like, at the time, right? But the thing is, it's hard to be passionate about something when you're just terrible at all, just one thing after the other, and you don't feel like you're getting anything, right? But the thing is, mastery unlocks appreciation. And I believe that, right? So the thing is, if you stay consistent, that is the real challenge, because this is going to get easier, and then you're going to realize, oh, I like this stuff. And that's when you'll discover if you have a passion for this, right? The concept itself is not that hard. It's just overwhelming. There's tutorials everywhere, and it's mainly the thing is about it is there's no immediate payoff, right? That's the trap about it, right? And also, you don't want to go down a rabbit hole, like I mentioned before. You could start off, let's say, one of the first things you want to do is learn Python. And if you just say learn Python without any context, you could go down a rabbit hole and learn a bunch of things you could do, or cool trivial things that you could do with Python, but it's not necessarily going to go towards your goal, right? So there's tutorials everywhere, but you want to make sure you have a focus on it. And the other thing about it is not immediate payoff. You have to build up for a while before you start seeing results. So, and that's the other thing, is that, because this is related, comfort kills urgency, right? If you're comfortable about something, right? If you already have a job and your lifestyle feels safe, then you're going to come one day and you're going to start skip learning, because I'm like, oh, I don't want to learn today. And because it has no cost, because if I don't do anything today, there's nothing bad that's going to happen to me tomorrow. I'm still going to wake up, I'm going to be comfortable, and everything's fine, right? And the problem is people wait until they're forced, right? That's when the sky's falling and you're like, oh, I need to do this now. That's when people start applying this stuff. And again, the successful people I see are the ones who prepare beforehand. Like I mentioned before, that the people that I saw that were graduating already had a job. They weren't, a year before you feel safe at school because you just wake up, you go to class, and you do what you need to do. You just go through your routine. But they created their urgency for themselves, where they're like, no, if I don't want to be panicking, and at the end of the day, during graduation, I'm going to have to put in all the work beforehand. So, and the thing is, most people wait until they're forced before they start panicking. And I have a friend basically that I knew that was in this case where he wanted to further his career, but he was already comfortable because his job was safe and whatnot. And then, no fault of his own, the company was downsizing, right? And now the company was pretty much cutting people, and he feel that he missed time of his window of opportunity to train and further his career. So the thing is about that, I would say, is to basically create urgency intentionally, right? Don't wait for a crisis. Find serious peers, find people who are serious about this, so you can build accountability. So you want to be ready when the opportunity actually comes. Here's your action plan. Tonight, start immediately. Set up Google Colab. Remember, just have a Gmail account where you can click on and you see like Google Docs or Google Sheets. There's more options there, and you have Google Colab. That's what you want to use there. And write your first Python script. Use any YouTube tutorial. Just get something running. Just get started, right? So this week, after tonight, right, this week, you want to do data processing. Build something. Just process any data set. Just go through the process from end to end. The quality doesn't matter. It's not important. The whole idea is that you get it done, right? So you know the process, you know these things exist, and you get the momentum, you get the ball rolling with it, right? The hardest thing is actually to get started and get the ball rolling. But once you start doing it, then it makes it easier to keep it going. Then month 1, right? That's where you start doing the data science stack, the foundations. So learn Python basics. So that's what you're learning, the Python scripts and the basic stuff of Python. Then you start going more specific to learn like the NumPy essentials and pandas workflows, and then the visualization of like Matplotlib or Seaborn. Then month 2, classic machine learning plus the different tooling. So scikit-learn, it comes with Python, but it has pre-built classical algorithms in there. You want to learn Git source control, so the code you work with, how do you actually iterate over that and keep track of it. Your virtual environment setups as well. So that way you don't have the problem like, oh, it works on my computer. So you can consistently make the environment and work anywhere. And Docker containerization is a way to take that and just kind of like load it up and everything works. So learn how to do all this stuff, right? Again, you can look up the basics on YouTube on this. And especially with the Google Colab, it's free. As long as you have internet access, you don't have to invest into like a powerhouse computer, put any money into it. You just chip at it little by little. This is your roadmap. Just go through this stuff, right? And then month 3, that's when you start getting to more like industrial, like heavy lifting, deep learning, and large language model tools. PyTorch, because the basic trainings of this, because PyTorch is the de facto, the standard of it. Mentioned before, learning the transformers of model architecture, get the concept how it works. You could look up the actual paper that kind of like changed everything. Go to Google, look up Google Scholar. Google Scholar just basically it's a Google search specifically for academic papers, and look up attention is all you need and read that paper. And then you learn like LangChain, get familiarity with it, so you could chain like large language models, work with Python and JavaScript. And these are pretty much like the modern AI tool. Get comfortable with that stuff, right? And here's where month 4, this is where it starts. Basically, you're putting the rubber to the road here. You want to start doing projects that will get you hired. So do 3 domain projects minimum and keep going afterwards. Use real data only. Don't use Kaggle data sets, whatnot at this point. You might be learning them, using them from month 1 and month 2 and month 3 to learn how this stuff works. But if you want to get hired, you want to use real data only and use end-to-end pipeline, how you get from the start to the finish in real world scenarios, and then show the business value in the domain. And at that point, from this month floor, apply to 5 jobs daily. Block out an hour every day, apply to 5 jobs. Not just tech jobs, anything that's using AI, look for like AI, ML, any of those keywords and apply for it. And at the team, so from this point on, just keep building while waiting, because at this point, you have enough of the foundation to start understanding how these things work, and you're only going to get real experience by actually doing real projects in real world scenarios. AI engineering is new and is now mandatory. So if you're not a non-adopter for this, you're becoming pretty much the minority of this, right? Like whether you like it or not, it's here. You should learn about it. And prompting is not AI engineering, right? ChatGPT prompts is not enough to be an AI engineer. You want to be able to look at real opportunities and actually build a system that solves that problem. You want to have a real business problem and have a solution for that specifically. You want to deal with real messy data that's representative of the actual data that the business or the problem will actually use, and deploy a model to handle that and get real results and the delivery on that, right? Value is what makes companies reach out to you, like showing like, hey, in our actual scenario, our actual problem, you could solve it. We want you to solve our problem, right? And the thing is about this as well, because AI engineering is new, reinvention is very normal. Reinventing yourself to become an AI engineer, going from one space to another, it's not only normal, it's an act of survival. It's not how it was like 30 or 40 years ago, where you have one job and you could just stick to it. Now things are changing so drastically that job positions are changing, that even if you have a job right now, you have to reinvent yourself to learn how to incorporate even AI, even if you're not necessarily using AI engineering, but using AI to help work with that. So in my example, I've reinvented myself many times. I started off as like a 3D artist, to a technical director, to a CG supervisor, to now the AI guy. And every time starting over feels like it's repeating that, like I'm starting all the way from the beginning and I know nothing, and it's a huge mountain to climb, but I learned to live with it and move on, because that's, if you want to survive, that's what you need to do. And the other thing is, start small. I know a lot of it is like a massive, you hear the massive things are changed, but most companies just needs a lot of small quality of life things that have massive impact. Like they have 20 years, 30 years of files that needs organizing. Just having a file renaming that's automatic, meaning they don't have to manually hire people or have the logistics or the overhead to manage all that stuff. And I tell you for a fact that I've done this many times, that this has a real impact for a company, right? Shot processing, and that helpers, like in my space, like as a CG supervisor or whatnot, not having to hire specific people or spend weekends trying to just deal with data manipulation and management, whatnot, having code or like data cleaning utilities. These have real values, and they don't have to be big. You don't need a big idea for this to work. These small things add up. The other thing is, avoid half-finished projects. Big project, half-finished big projects. Your best work's your finished work. Having a lot of small projects that are useful are much better than a non-finished big project that's sloppy, that doesn't do anything, right? Other thing is, learn just in time. Learn what you need when you need it. Clarity beats clever code, right? Basically, if they understand what it does, understand the impact, that is what it comes down to, instead of how do you basically you code this without using 24 loops or something like that. And if you focus 3 to 4 months on real focus on actual what I laid out in the roadmap, actually something useful, not dabbling, not going down rabbit holes and just going through one YouTube to another just because it looks cool, one YouTube tutorial to another because it looks cool, right? That's when you start seeing like transition and momentum for this, right? So to help with that and make sure you're not actually going down a rabbit hole, I suggest you make what's called SMART goals. So SMART stands for specific, measurable, achievable, relevant, time-bound. So specific means it's clear and focused. What exactly will you do? Measurable, you can track it, right? How do you know it's done? Realistic. Achievable is realistic with your current resources. Hard but possible. Like you make a goal that actually you could achieve with your current resources, right? Relevant, actually matters to your bigger goal, moves your life or career forward. So you might make sure a goal that actually feeds into your bigger one as well. It's time bound here, right? So it has a deadline. So by when? So an example of it, most people make goals, say like most people don't even make goals at all. They just they go like, I want to learn AI. That's it. That's as far as they want to go, right? And they go on YouTube and just say, I want to learn AI, and just go down rabbit hole after rabbit hole. But it's not specific, because at the end of going through all those tutorials, what can you actually do? What do you actually learn? Here's a SMART goal version of this is, I want to build and deploy one scikit-learn model in 30 days, right? So at the end of this, if you could say you could do this, now you actually have a headline, an actual tangible skill that you could use, as opposed to like learn AI. Like, what can you do with that? Now, if you have this, now this specific skill set might be useful to someone, right? And so the thing is, most people will delay, right? They'll wait till they feel ready, and they'll go into like another course or another YouTube tutorial, and they'll do 6 months of like planning and whatnot. If you want to actually succeed at this, you must actually start today.